Aboagye from Mississippi State University, doctorate student, and he's going to talk about the effects of hypoxia and temperature on hypoxia tolerance, oxygen consumption rate, and swimming performance in juvenile paddlefish polyodont specimen. Thank you.
All right. Good afternoon, ladies and gentlemen. As Dr. Min said, I'm going to talk on the effects of hypoxia and temperature on hypoxia tolerance, oxygen consumption, and swimming performance in paddlefish. I'll briefly talk about the importance of oxygen and hypoxia in aquatic systems, give you my objectives, methodology for, I did basically 3 different experiments. So what I'll do here is give you the methodology and the result for each one, and I go to the next. Give you a brief discussion, then research implications. So basically what we're talking about when we talk about hypoxia is low oxygen concentration. That's when rate of oxygen consumption is more than is greater than oxygen production in the system. The opposite of that is normoxia. That's when the aquatic system is fully saturated with oxygen. The problem of hypoxia basically has to do with the fact that water has low oxygen solubility when you compare it to air. Oxygen diffuses more slowly in water than air. When you combine these 2 factors with excessive nutrient input from agricultural lands, eutrophication here, you combine this with increasing temperature, which causes increased respiratory oxygen demand, as well as water density stratification. The problem of hypoxia becomes even worse. Unfortunately, this is not going to get any much better very soon, because the world population is increasing, meaning we need to produce more food, meaning we have to clear more lands for agriculture, as well as the problem of global warming, which is increasing temperature of surface waters. I won't go much into this paddlefish biology because we've talked about some already. Basically, for those who don't know, it belongs to the other aspersiforms with sturgeon. It's in the same family with the Chinese paddlefish. Migrate great distances to spawn.
Can you speak louder?
All right.
Some of us don't hear so well.
All right. Sorry about that. The goal of my research, go ahead. The goal of my research is basically to gain an understanding of physiological effects of temperature and hypoxia on paddlefish. We are doing this basically because there is little information on juvenile paddlefish respiratory physiology. Another thing is paddlefish has total dependence on aquatic respiration. That's one of the few fish that do that. Some populations are also found in hypoxia-associated habitats. Where I got my what you call the brood fish, there's the oxygen profile of the system I got my brood fish from, and as you can see, the DO profile goes down on that area. But more importantly, paddlefish have a high economic value. Dr. Mills have already talked about that. So we thought we might want to know the oxygen implications for the hypoxia implication for that. So my first experiment was to understand the minimum hypoxia threshold for paddlefish. And we got a broodfish, as I said, from the Nosby National Wildlife Refuge in Mississippi. We had 2 treatment temperatures, 18 degrees Celsius and 26 degrees Celsius. Basically, this is the temperature range for the refuge. We had 6 replicates, 8 fish per tank. The fish were about 10 grams. What we did was we did a stepwise DO degradation. As you can see here, what we basically did was we had the fish in the tank, dropped the DO level from 149 millimeters of mercury at a rate of 15 millimeters per mercury every 5 minutes. Then we hold the fish there for 20 more minutes. If the fish survives, we go down again using the same rate until 50% of the fish lost equilibrium. What we found out was that the threshold, minimum threshold PO2 here, partial pressure of oxygen, increased with temperature. But the interesting point here is when you convert this to milligrams per liter, you find out that it's the same, around the same, like 2 milligrams per liter, which is to say paddlefish in an acute hypoxia concentration will lose equilibrium around the same milligrams per liter. Our third experiment, having seen this, we try to understand the oxygen consumption at these different partial pressure of oxygen. We had the same size of fish, the same treatment temperatures. We put the fish in intermittent respirometer and had 7 successive water PO2s, but that's 149. Degradation using the same rates. What we did was have the fish in the respirometer, let it acclimatize for an hour, measured oxygen consumption. As you can see, the fish was free to move in the respirometer. Measured oxygen consumption, then we did it 3 times, 7 minutes each time. Then go to the next level until we got to 59 for both temperatures. And this is what we found out, very interestingly. Within the same temperature, we found out that oxygen consumption for fish at 26 degrees Celsius was about the same, no significant difference until we got to 89. From 89 millimeters of mercury, oxygen consumption started decreasing very, very fast until it got to 74. At 74 millimeters of mercury, fish just went out. They lost equilibrium, and some of them actually died. So what we found was the critical critical partial pressure of paddlefish. By this we mean that's the partial pressure of oxygen that paddlefish metabolism is no longer supported by aerobic respiration, but rather anaerobic respiration. So for at 26 degrees Celsius, we found it to be at 89. For fish at 18 degrees Celsius, we find it to be at 74 millimeters of mercury. And surprisingly, just like the first one, when you convert this to milligrams per liter, it's almost the same. It's around, let's say, approximately 5 milligrams per liter. So what that means is at, let's say, 5 milligrams per liter, paddlefish metabolism is no longer being supported by aerobic respiration, but rather anaerobic respiration. And what we found from other literature is that paddlefish is really not good at anaerobic respiration. So what that means is, at all costs, we try as much as possible to keep DOs above 5 milligrams per liter. In terms of oxygen consumption, we found out that at all PO2s, fish at the higher temperature, 26 degrees Celsius, consumed more oxygen than fish at 18 degrees Celsius. The third experiment was to determine the effect of acute hypoxia on active metabolic rate. We've found out oxygen consumption at stable standard rate, so we're trying to find how much oxygen do they consume as they swim. The fish were much bigger at this point. They were at 20 grams. We had the same treatment temperatures, 18 and 26. We had just 2 PO2 treatments, 148 and 59 plus or minus 3. What we did, this is a swim flume. What we did was we have the fish in here. You can see the size of the fish. The respirometer is blocked to keep the fish in there. We put the fish in there. We adjust the speed of the respirometer here. We put the fish in there at 10 centimeters per mercury. Measure oxygen consumption at that rate, at that point. Then increase the speed by about 5 centimeters by 5 centimeters per mercury, 5 centimeters per second. Measure oxygen consumption there. Then we go on until the fish loses equilibrium, and that's what we call the Ucrit. That's the maximum swimming velocity that the fish can attain. What we found out was For pneumosia, that's for high oxygen content, fish at 26 degrees Celsius has a higher Ucrit. That's they can swim at a higher velocity. That was around 55 centimeters per second, compared to fish at 18 degrees Celsius. However, in a hypoxic situation, there was no significant difference between temperatures. It doesn't matter what the temperature is. When the fish is in hypoxia, they are not swimming. We found that hypoxia decreases Ucrit, that's the maximum swimming velocity, by about 24% in 18 degrees Celsius and about 41% in 26 degrees Celsius. In terms of oxygen consumption, we found out that fish at 26 degrees Celsius consumes more oxygen at all the velocities we measured compared to fish at 18 degrees Celsius. In hypoxia, there was no difference. There was no difference between the temperatures. So basically, in conclusion, what we found out was paddlefish are relatively sensitive to hypoxia. They have a critical PO2 of around 5 milligrams per liter and minimum oxygen threshold of about 2 milligrams per liter. Paddlefish in hypoxia exhibit a reduction in swimming capabilities. What this means is paddlefish are able to reduce their metabolic rate, thus potentially increasing their chances of surviving in hypoxic situation. However, as we saw, the swimming capacity is highly reduced, suggesting that the ability of the fish to escape a hypoxic situation is highly reduced. This is made worse by increasing temperature, which increases the PO2 crate and as well as the PO2 threshold. So the combined effect of temperature and hypoxia may not only reduce paddlefish habitat quality, but may reduce its quantity as well. Basically, my thanks go to Mississippi State, my thesis committee members, my lab mates, and staff of the private John Allan National Fish Hatchery, where they helped me with the fish, as well as Dr. Mims. Thank you. Anybody has any questions?